Vectors. By the end of this lesson, we'll be able to describe a vector or scalar using magnitude and direction as appropriate. We'll be able to describe a vector sum in one dimension, and we'll be able to describe the perpendicular components of a vector. To get to those objectives, we need to know that scalars are quantities described by magnitude only, while vectors have both magnitude and direction. Vectors can be visually modeled as arrows with appropriate direction and lengths that are proportional to their magnitudes. Distance and speed are examples of scalar quantities, while displacement, velocity, and acceleration are examples of vector quantities. Vectors are notated with an arrow above the symbol for that quantity. When determining a vector sum in a given one-dimensional coordinate system, opposite directions are denoted by opposite signs. Combining the motion of an object and the motion of an observer in a given reference frame involves the addition or subtraction of vectors. Vectors can be mathematically modeled as the resultant of two perpendicular components. Vectors can be resolved into components using a chosen coordinate system. Vectors can be resolved into perpendicular components using trigonometric functions and relationships. Some vocabulary. Resolve means to break apart a vector into its components. A component is a part of a whole vector. For us, there will be one component for each dimension, x, y, or z. AP Physics 1, we deal with just x and y. A resultant is the vector that is created by combining all other vectors. Vectors can be mathematically modeled as the resultant of two perpendicular components. Vectors can be resolved into components using a chosen coordinate system, and vectors can be resolved into perpendicular components using trigonometric functions and relationships. Resolve means break apart a vector into its components, and a component is a part or a piece of a whole vector. For us, there's going to be one component for each dimension, x, y, or z. AP Physics 1, we only deal with x and y components. The resultant is the vector that is created by combining all other vectors. Antiparallel, parallel but in the opposite direction. A comprehensive list of vectors we're going to see throughout this entire year. Of course, displacement, velocity, and acceleration. We also have force as a vector, momentum as a vector, impulse as a vector, torque, angular momentum, and angular impulse are all vectors. So everything you learn in this lesson is going to be applicable the entire year whenever you're dealing with vectors, especially if you're dealing with vectors in two dimensions. Just remember, if you are dealing with a vector in two dimensions, or they're acting at an angle, break them up and always treat the x-axis separately than the y-axis. When dealing with vectors, direction is important, so we shouldn't forget to define our coordinate system, which is normally right, positive, up, positive. Next, we can combine two vectors by moving them in the same direction, as long as we move them without changing the angle. We call this combining them tip to tail. This combination has created a larger vector, or a vector with a greater magnitude. On to subtraction. If we are subtracting, then we can add the antiparallel vector. It's the same thing as adding a negative. For instance, 3 minus 2 is the same thing as 3 plus negative 2. So the antiparallel is just the parallel vector, but in the opposite direction. This combination has created a vector magnitude of 10 meters to the left, or negative 10 meters. If we have vectors in two dimensions, we can still do the tip to tail as long as we move that vector without changing the angle. Then we get the combined magnitude to be 20 meters in this instance. Now, if we have two vectors that are at different angles, vector x1, or delta x1, our displacement in the blue, or the cyan, is at 45 degrees above the horizontal, and vector 2 is 10 meters at 0 degrees above the horizontal, so exactly along the x-axis. Let's say we want to find the net displacement of these two vectors. Because vector 1 is at an angle and vector 2 is not, we have to resolve vector 1 into pieces that make it up. These are called components. Vector 1 is going to go to the right and up, so we should expect the components to go up and to the right. Closer look. Drawing these dotted lines is how we resolve this vector into its horizontal and vertical components. Every time we do this, we make a right triangle, and we love right triangles because they're easy to solve. Remember this, SOHCAHTOA. Remember this is sine times sine of theta equals opposite over hypotenuse, cosine of theta equals adjacent over hypotenuse, and tangent theta equals opposite over adjacent. Adjacent means the side touching the angle, hypotenuse is the biggest side, and opposite is the side not touching the angle. For the y component, we're going to use sine theta equals opposite over hypotenuse because that is our opposite side. Let's say I want to solve for the opposite side. I'm going to multiply hypotenuse to each side to get hypotenuse times sine theta equals my opposite side. Or in other words, the magnitude of the original vector, which was 10, times sine of the angle, which is 45, that will give me my opposite side. But wait! For triangles, we'll use degrees. For circles, we use radians. Triangles are an equal division, degrees are an equal division of a circle, which is mathematically useless. And circles, the radian has a very specific definition based on a circle. So when we deal with circles, we'll get to that again. But for now, make sure your calculator is in degrees before trying to do this calculation. All right, so we should get something like 7.07 because maybe you know sine of 45 is 0.707. Well, let's figure out this x-axis component, or the adjacent side of the triangle, which is right here. Again, I'm going to get adjacent all by itself by multiplying hypotenuse to each side this time. So it's hypotenuse times cosine theta, or the magnitude of my original vector, which was 10, times cosine of 45. And again, we have to wait to remind ourselves to check your calculators. You may be getting wrong answers, and you may not recognize that they're wrong answers. Make sure we're in degrees. This is extra confusing because at this point in the year in your math class, you are using nothing but radians. So please double check every time you go into math or physics. Now we're ready to add the x and y components. How do we add x and y components? Take our x component and we can add it to the other vector, which is already along the x-axis. Remember, we have to treat the x stuff separate from the y stuff. So we can add 10 plus 7 to get this 17.07 meters as our magnitude in the x direction, or the x component. To get the y component, we already have the 7.07. When we add the x component to the y component, we have created this right triangle. And to combine the x component and the right triangle, we use Pythagorean theorem to figure out that hypotenuse. And that hypotenuse is going to give me my resultant vector. And notice in the bottom right down here, my resultant vector can also be found using the tip-to-tail method. It's just we can't get the exact mathematical magnitude. But for direction, absolutely. When we do Pythagorean theorem, it's r, the resultant vector, equals x squared plus y squared, and the square root of that. So my resultant magnitude is 18.47 meters. To calculate direction, we're going to use the direction formula. The direction formula, because we have my adjacent side of the triangle and the opposite side of the triangle, we're going to use tangent theta. Tan theta. To get tan theta all by itself, we're going to multiply each side by the inverse of tangent. And we get theta all by itself, which will give us our direction, an actual number direction. And rather than use opposite over adjacent, because my opposite side is my y, and my adjacent side is my x, I will use theta equals the inverse tangent, arctangent, y over x. This is called the direction formula. When I plug all of that in the calculator in degrees, I should get about 22 degrees. All right, to recap, we need to know that x and y have to be treated separately and completely independent of one another. If a vector is at an angle, resolve it into x and y components. To get magnitude of the resultant vector, add x and y components with the Pythagorean theorem. To get the direction of the resultant vector, use that direction formula. Something that may be useful for the entire year is to think about this, where we have cosine written along the x-axis, and then sine sharing that s. Well, the reason why this is useful is whenever you're dealing with something that is exactly on the x-axis, and you need to find the x component of a vector at an angle, we're going to use the cosine function. Whenever something is directly along the y-axis, we're going to use the sine function. So maybe this will be useful at some point, or not. If we look at this example, a cat is launched 30 degrees above the horizontal axis with a velocity of 30 meters per second. How long will it take for the cat to reach its maximum height? Here we have a cat launched 30 degrees above the horizontal axis with a velocity of 30 meters per second. How long will it take the cat to reach its maximum height? This is a vector. A velocity is a vector, so 30 meters per second at 30 degrees relative to the ground. When this cat goes through the air, it's going to exhibit this parabolic motion, as we've seen before when objects have been in free fall. So pretend like this is a nice symmetrical parabola. The reason why this object is going down in a curve is because of the acceleration that's happening. And our acceleration is happening because we are within the gravitational field. So negative 10 meters per second every second that goes by. Meanwhile, we have this velocity that's launched at an angle. Well, this acceleration in the y direction will not affect your acceleration in the x direction. We treat x and y separately. So we need to figure out what is our velocity in the y direction. And I know that whenever I'm dealing with vectors at an angle and I'm looking for the vertical direction, I can just use my hypotenuse times sine of the angle. My hypotenuse in this case is 30 times sine 30. When I plug that into my calculator, in degrees, I get 15 meters per second. So now this becomes just like those other free fall problems, where we try to figure out how long is it going to take to get to zero. If my initial velocity is 15 meters per second upwards, and my acceleration is in the opposite direction, negative 10 meters per second every second, then how long is it going to take? After 1 second, I know my velocity is going to be 5 meters per second because it started off in the y direction as being 15. So 1 second later, with acceleration in the opposite direction, I've lost 5 meters per second. After another half second, then I know my final velocity equals 0, and I'm now at my maximum height. So I've gone 1 second and a half of a second. So t should equal 0.5 seconds. Next up, make sure you practice. For more practice, there's your AI prompt. Don't forget to ask each other, ask me, and keep asking until you get it.